Morning. Good afternoon. Let's start the lecture. Okay, so we're gonna talk about a new topic today now. In previous lecture, we finished failure due to static loading. Okay, so from today's lecture, we're going to talk about the failure due to fatigue loading. All right? Yeah. Just a few words about a fatigue. I guess everyone knows what a fatigue means. You go tired, right? And when you get tired, dangerous things happen. Okay, so like a news title says, yawning almost killed a man. Metal can get tired too. So when metal get tired, disaster happens, right? Yeah. So essentially, the force of nature is really strong. So it works on everybody, everything. Okay. So the question is, what is fatigue, and what causes this fatigue failure? Right. Yeah. So in short, generally, basically, when you see something failed due to fatigue loading, okay, normally that means the thing has been worked or has been used for a long time, right? But theoretically, what the fatigue is, it's a progressive damage or fracture of a material caused by repeated cycles of stress or strains. Okay, so that's a sort of a simple definition right here. Okay. The keywords is progressive, okay, and here is repeated cycle of stresses or strains. So that's the keywords of fatigue here. So it's not something that will happen, you know, in 1 minute or 2 minutes in a very short period. Okay? It generally will happen after a certain long time, or after a certain number of cycles. So this diagram here shows you the different kind of cycles of stress that we're going to be dealing with here. Okay. So let's say you subject your parts or material to this kind of cycle of stress. So what we call this is so-called fully reversed stress. So what is fully reversed? Because it goes to maximum, then minimum, maximum, minimum. So the magnitude of the maximum, minimum, they're the same. So that's what they call fully reversed, right? Yeah, this is called fully reversed. So if this is the sigma max at here, okay, so this axis is sigma at here, right? And then this axis is this one here is sigma mean. Okay, so sigma mean equal to sigma absolute this equal to that, and the mean value here is 0. Okay, so that's fully reversed. Okay. And the other type is so-called repeated. So for repeated, this is a special case. Basically, it goes up and it come back to 0. Okay, exactly at the 0 here. So it's a 0 here. I mean, not here 0. This is 0 here. Okay, so that's repeated here, and this is a sigma max at here. So you have a sigma mean at here. So there's a mean value exists in this kind of case. And then this one here is a so-called fluctuating stress. Okay. So in this particular case, your sigma max, okay, and sigma mean, okay. So basically, sigma mean is not 0, okay, yeah, and that's called fluctuating kind of loading. This is more of a general case here, right? More general case, because you see, for this particular case, if this is sigma m here, if you set sigma m equals to 0, you come back to here, right? Come back here. So this is more of a general case here. And ultimately, what we're gonna end up with, some design equations, okay, dealing with this fluctuating case. But we're gonna start with this one here, okay? So today's one, we're gonna look at this basically. When a part is subjected to fully reversed cycle, okay, and that kind of a fatigue loading, and what will be the failure? What will be the failure equations? Okay, and what will be basically the way to calculate safety factors? Okay, yeah. But no matter what, it's a cycle. So basically, it's working on it. Okay, sometimes working is a positive, sometimes it's a negative stress. But either way, you're going to work on the material, and the material will feel this kind of progressive damage. Okay. Yeah. What's more important for you to realize is fatigue loading. Okay, is different from static loading. So how different it is? Static loading, you can see the thing before bad thing happens. Basically, when you're subject to static loading, you see, oh look, it's yielding, right? It has this permanent deformation. So you immediately know you're probably not going to use the parts anymore, right? But fatigue loading, the tricky thing is, it doesn't happen, and if it happens suddenly. So it doesn't show any signs before it happens. Okay, so that's basically the tricky thing about the fatigue loading. Okay, and most of the cases of failure in reality is due to fatigue failure. Okay, so that's fatigue loading. And one more thing about fatigue loading is every material has a so-called strength. That's a yielding strength, or ultimate strength, right? Has this property of the material. Now, if you subject the material with kind of a stress, let's say this kind of stress, and you know that the maximum value, okay, it's actually lower than the yielding strength, okay, than the strength of material. So you think you're safe. However, because of this cyclic kind of stress, the material actually fails, even if the stress is well below the yielding strength. Okay, the reason is just basically because now it's not a static, it's a cyclic kind of loading. Okay, so that's the danger about the fatigue failure. So when fatigue failure happens, it generally will cause a catastrophic kind of failure. Okay, so there, I'll give you some cases, some pictures shortly. Okay, yeah. So guarding against fatigue loading, okay, is part of the important concerns or that you have to consider when you design for things. Okay. So now let me just kind of touch upon a little bit about the mechanics of this fatigue process, right? So in your more advanced mechanical engineering courses, you have a standalone course called fatigue mechanics. Okay, so basically they talk about the whole process, the whole mechanics of fatigue failure, right? But in short, there are three things got involved, okay, for fatigue process. First, the crack initiation, crack propagation, and then fracture due to unstable crack growth. So what does that mean? I'll use this one here for to illustrate what I mean here. So there are three stages basically. So there are three stages. Okay, so there's three stages regarding fatigue process. Okay. So crack initiation. Fatigue failure always start with a crack. Okay, with a crack. So where's the crack from? The crack can be from different reasons. They could be because of this manufacturing process. And when you buy a material, so the material maybe is cheap. Right, it's pretty cheap. So you buy it, but it's probably not properly manufactured. There are some small porous holes inside the material. So those are basically the starting point of a crack. And the other reason may be because the material are not manufactured according to the standard. For example, you have a certain kind of irregular geometry change. And that basically causes what we call in the last lecture what? Stress concentration, right? Yeah. And as a matter of fact, most of the crack initiation started at this location of which having this stress concentration. Okay, so that's where you have a crack initiation. As a matter of fact, this is a sort of a research area. People trying to look deep into this material as to how the crack really started in the molecule kind of a level there, right? Yeah, so that's not our course, but we just have to know there's crack initiation. Okay, it's the first stage of the fatigue process. Okay, so for example, in this picture right here, this is a bending fatigue failure part. Okay, so the starting point of this fatigue Okay, starts somewhere here with this red arrow location, right? Yeah, and that's where it gets started. Okay, it's being amplified. Not sure how much here, but it's quite a big amplification using the so-called scanning electron microscopy image here. One of our professors has bought similar equipment at here, so it's actually the only one in BC. So it started here, and then the second stage is the crack propagation. The propagation, you get to understand is, okay, the crack only propagates when it's under tensile stress. Okay, so that's basically one of the things that you need to understand. This portion here, so only propagate under tensile strains. Okay, under tensile stress, right? Okay, yeah. So essentially, if you look at the back at it here, okay, look at the back here. This is your cyclic stress at here, right? So where is the tensile? Only this portion is tensile here, right? And this portion is compressive. Is that good? Yeah. So imagine you're bending a piece of wire, right? So how are you going to bend the wire? So one way that you evenly apply this is what we call what? Completely reversed loading or stress, right? Or maybe you're not applying it evenly. You're probably just applying like this, right? Like this. So when you apply like this, which means you're more of a positive for the bottom of this piece of wire, it's tensile, right? It's tensile. But on the top, on the other side of the wire, on the inner side of the wire, it's compressive. That makes sense? Yeah. So the crack propagation only happens when it's under tensile. So every time there is a tensile stress showed up, and there is a slight crack propagation. Essentially, it's like a progressively, the crack will start to enlarge itself, right? That's basically the second stage, crack propagation. Okay. So as you can see in this picture here, and this is what we call the so-called beach marks. So you can see this crack propagation as going along here. So this piece of wire probably is bending like what I said here. So most of the tensile stress is at the bottom here, right? So it's bending like that due to the normal stress. So it's propagated like this, okay? Propagate. And until at a certain stage over here, and this is basically the last one here called fracture due to unstable crack growth. So the crack becomes larger and larger, and until the end, it just cannot endure this stress anymore. That's what you call the straw, the last straw on the camel's back. And at that stage, you have this so-called sudden fracture. So this whole piece will fracture at this is sort of boundary here, and this whole area shows this basically the fracture of this wire, right? Yeah. So I think everybody has to play the game. You know, you have a piece of wire, you're trying to bend it. Let's break it, right? You keep bending it until the end it breaks, right? And it breaks. Okay, yeah. So this is the three stages of this fatigue process here. Okay, yeah. So that's enough. Just understand this three stages. That's good enough. Okay. And here's another diagram here. It's a picture taken from a NASCAR suspension failure. Okay. In this one, the difference here is the crack actually initiated from multiple points or multiple origins at here. Okay. Yeah. So the previous one has only one origin. So this one has three different origins. Okay. Because of the multiple origins here, and there's this so-called racket marks, right? So it's not very even surface at here, right? Yeah. But similar process as before. You have the crack propagation, and until at one point it just breaks suddenly. Okay, yeah. So that's another one here. And this diagram here shows you this so-called crack propagation process. So you see all these marks that are here, those patterns. This is what we call striations. Okay, striations. So each striation or each wave, it's like each wave right here, it's due to one cycle of this stress. Okay, one cycle of the stress here. Okay? This is so your loading may not be as beautiful as a sinusoidal curve, right? So maybe it's pretty noisy like this. So that essentially will give you a different look or different patterns of this striation set here. Okay, yeah. So the fatigue loading happens, actually once to me too. I had a bicycle when I was a graduate student at UBC. So I was using it on campus and happily, and all of a sudden, I just feel this thing doesn't work anymore. You just like you keep pedaling it, so this doesn't work anymore. So guess what happened? The rear wheel, the shaft, right? It breaks. Yeah. So it basically the rear wheel, the center shaft, right? It breaks. Yeah. It's been using for a while, and I took it apart. And clearly, I have no idea about the fatigue failure at that time, but it breaks, right? Yeah. So that happens a lot. Actually, the other part of the other part of a bicycle that can easily subject to fatigue failure is the crank at the paddle location, right? When you paddle, there's a crank. Yeah. So that part sustains this constant torque and bending moment. Okay, so that part, I have a picture in the lecture notes. I think you can take a look at that, how that feels. And here's an example here. Here's an example showing you this catastrophic kind of a fatigue failure. Okay, so if you read it here, on November the 2nd, 2007, it's a Missouri Air National Guard F-15C. So that's a Tomcat kind of airplane, right? It crashed when the upper right longeron failed during air combat training. So the longeron basically talking about it's a beam. Okay, it's a very important beam supporting the structure of this airplane at here. Okay, so this is the longeron here, and the upper right basically, if enlarge that, that's referring to this location at here. Okay, upper right. So that location cracked and the airplane failed during the combat training. Okay, here is later they did a little simulation simulating the airplane's failure process. Okay, and the moment of the failure. So this is not real, right? This is the computer simulation. Watch how it happen next. Yeah. It's pretty sudden, right? Yeah, so nobody would anticipate that thing to happen. Okay, yeah, and fortunately the pilot survived. So this example shows you what I said. Fatigue failure is dangerous. It's sudden, right? And you don't see that because you don't see this thing. Visually it's not seen. It's discernible, right? So then what happens is people at the end did some check and then look into the reason, right? So what's the reason for causing this failure at here? Okay, they actually find similar reason in many other aircraft. So in the end, what they find is, okay, it's the thickness, okay, of these parts here are not manufactured properly according to the blueprints. So the manufacturer, reduced the thickness of the longeron at here, right? Reduce this one here, or what they call is where there is a surface roughness that could cause stress concentration, right? You can see this. The stress concentration is almost everywhere, right? Yeah. So you got to be careful basically about this when you design things. This is always you got to keep in mind as to this fatigue failure, all right? Yeah. So that basically brings us to the next level of question. Okay, so we understand there are different other examples. Okay, take a look at the lecture notes in your textbook as to the examples of fatigue failure. But from an engineering point of view, okay, so now I understand the importance now. So how am I going to design against the fatigue failure, right? So that's more of our purpose here. Okay, So one way of doing this one here is, okay, so it's just like a static loading. When you have a static loading, you know, as I said, we basically compare the stress with the strains, right? Yeah, so then I have to know what the strains is for the material. So you do a tensile test to get the strains, right? So that's the static loading. So same thing at here. If I'm going to design for fatigue loading, I have to know the so-called fatigue strains. Okay, fatigue strains. So how do we get that kind of data here? So we do this kind of test here. Okay, yeah. So this test here, there are different ways of testing the fatigue strains. Okay, so this one here is so-called RR Moore rotating beam machine at here. This machine actually you will use it in your fourth year mechanical engineering lab. Okay, there is a standalone testing here, so we do have one in the lab here. So what this machine does is it tests on a so-called test specimen. This is the test specimen here in the middle here. Okay, it's manufactured according to standard, and with a standard diameter in the middle, 0.3 inch. The surface has to satisfy the standard surface. Okay, so grounded. Okay, then you have also the radius of this curve here, so it's everything standard, and you mounted this specimen, okay, onto this machine at here, and then adding some amount of weights at here. Okay, so this weight doesn't have, this weight can be changed. Okay, you when you do experiments, you can change this weight. So basically, then there are two bearings at here. So if you look at this system at here, okay, and if you do a free body diagram, so let's see what happens is this is the weight at here. Then on these two ends that are here, you will have, right, because it's even in the middle here, so if this is W, so you will have half of W here and half of W here, right? Yeah. And then you have this two bearings simply support the two bearings here, so you will have two supporting force, okay, at these two locations. That makes sense, right? Yeah. So if this is A and if this is B, because the geometry is all even or symmetric, so this side here is W over 2, and this side here is W over 2. Okay? Yeah. So if you look at this one, if you look at this free body diagram in here, and we actually learn here, so between A and a B, what do we call this? Pure bending, right? Exactly. Between A and B, you have this pure bending situation. Okay, so this is basically the location of this specimen here. So the specimen subject to the pure bending here, right? Okay, so A and B, okay, subjected to pure bending. Okay, yeah. So if it's pure bending, then if I cut a cross section anywhere between A and B, okay, so if you look at the cross section here, it's a circular. Now, what we're interested is, okay, we're interested in how the stress, okay, varies on the cross section at here, right? Yeah. Now remember, the motor is keep spinning. Basically, the specimen AB or the bar at here is keep rotating at here. Okay. Now, if let's say consider, we know that when it's subject to bending, maximum happens on the top or the bottom, yeah, right? Yeah. So if I look at the location, let's say instead of calling A here, let's look at the location. Let's call it P point here. Let's look at this location P, right? Look at this location P. So the location P, okay, when it starts to rotate, the location is over here, right? And it's rotating. So the next moment, the P will, if I look at the front view here, the first is here, and the next moment P is here. Then the next moment is here, 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 right? So the P changes, right? The location changes as the shaft rotates. That make sense? Yeah. So what is the bending normal stress at this location P? In general, what's the bending normal stress? It's what? M multiplied by R divided by I, right? But actually, it's not R, it's actually what? R, when we in static analysis we said R, that's the radius, right? This is R here, right? This is R here. But I'm talking about this. It's a bending normal stress at the P at arbitrary location. You see that, right? At the arbitrary location. So essentially, that formula is actually, you should use a so-called C here. So what is C? C is the location between the neutral axis and, so this is the C here, okay, between the location of the P. Does that make sense? Yeah, that's the formula, right? That's the formula. So if you start at the P here, if you start at the P, then let's say this is the drawing of the sigma, okay, at this location P. If you start at a P, the C value is R, right? And that's actually the maximum, isn't it? Right? So it starts at maximum. So when the shaft starts to rotate, and then the value or the bending normal stress will start to decrease because the C value will decrease. Okay, will decrease. So basically, it'll start to decrease until it hits this location. That's a 0, right? That's a 0. Okay, and then it goes to negative, basically over here. Okay, and then come back. Okay, so that's the distribution. And if you're rotating, if your constant rotations over there, okay, you will see this kind of a change here. Okay, yeah. So that's called cyclic. So this is basically what we call completely, right? You see, this is called the one where we see the completely reversed, okay, loading. Okay, completely reverse loading. Okay. So the structure or the setup of this RR rotation Moore machine at here give us this completely reversed loading on the specimen at here. Okay, so that's the purpose of this RR rotation machine. Okay, so then what does it do then, right? Yeah, basically you don't change the weight. You put some amount of weight over there, then you let it to spin, right? Let it spin. So you know the spin with RPM. So basically you have the counting of how many RPMs goes by, right? As it's working. And at a certain time, right? At a certain time, so this part will fail. Okay, basically will break, right? Yeah, that's where we see the maybe it doesn't break, but anyway, if you give enough weight here, giving a good stress, okay, it will break. Okay, it's still here. So then, in the end, what you do is, okay, what you do is you draw a diagram here, basically. Okay, you draw a diagram. So let's say, for example, right, you have this sigma, you have this number of cycles. Okay, so 2 columns here. So the first column you record, maybe I'm gonna subject to 100, let's say KSI or SI, doesn't matter. So it depends on the situation. Then you record, I don't know, maybe this is 100 cycles, right? 200 something, 300 something, right? So then you record it or draw it or plot it in the diagram here. So this is number of cycle. Okay, this is the stress, right? Stress. Okay, so you can plot them out on the diagram here. So it more or less look like, okay, more or less look like this. Okay, if it's steel, it generally will flatten out at here. Okay, yeah. So that's the purpose of doing this test at here. So I'll explain what this is, but this is what we call is SN diagram. So stress and number of cycle diagram. Okay, so through experiment you can obtain this so-called stress and the number of cycle, okay, diagram. Okay. Yeah. So everything else basically starts from here. Okay, stress and number of cycle diagram. So sometimes we also call the stress life. Okay, stress life diagram. Okay. Yeah. So good. Okay. Yeah. So one of the capstone design project this year that I'm supervising right now, it's the students are working on a project from a local company. So they are interested in construct a machine to test the machine's fatigue failure, and they have a standard sample. Basically, the machine, I'm not sure where the sample is from, but they're really interested in that particular sample, particular material, and a particular shape, and trying to all their purpose is trying to basically apply certain loading until it fails. They actually don't want to, they just want to see it breaks. Okay, and they wanted to design a machine so the parts will subject to a constant twisting, basically torque, and plus a basically a reversed or a fluctuated tensile stress on the part, right? So the students are designing a machine of doing that. Okay, yeah. So this is the diagram that I was just showing here. This is more from practical data here. It's from textbook. Okay, so all the dots refer to the failure points here, right? I'll refer failure points. Okay, yeah. So if you look at the first dots, actually it's quite easy to understand. What's the first dot? The first dot basically it failed at where? 10 to the power of 0. Basically it failed in one cycle, right? In one cycle here. And it failed at what value? At where? As ut, right? Does that make sense? Yeah. So what this axis here is so-called stress. Remember, that's the stress that failed by the part. So when the stress is SUT, apparently it's gonna basically a break, right? Fracture. Okay. Yeah. So if you change the stress, you will have all of these values here. So this sigma A at here, okay, that's the value of this amplitude. Okay, if I go back to my diagram here, what's the sigma A here? So sigma A, this is sigma A. Okay, this is sigma A here, right? Yeah, amplitude. Okay, yeah. Okay. So a couple of things from this diagram. Okay, this diagram first of all is for material steel here. Okay, it's for steel. Okay, I'll tell you why it's steel. Because only for steel you will have this so-called knee point at here. This is called a knee point. Okay, it's flattened out at here, right? Flattened out essentially means if you subject the parts to a stress, in this case 50, right? If anywhere below this 50 at here, so what can you deduce from this diagram? You never fails. Exactly. So it doesn't matter how many cycles it's going to subject it to, it's not going to fail. That's what we call it's going to have infinite life, right? It's going to get infinite life. And this is a phenomenon for steel. So now back to this number of life now. So that's what we call low cycle, finite life, and infinite life, right? Yeah. So you can see the definition clearly. Lower than 1,000, it's called lower cycle. Between 1,000 and 10 to the power 7, okay, 10 million, okay, it's called finite life. And to be larger than 10 to the power 6, it's infinite life, right? Yeah. So there is a little overlap between this finite life and infinite life here. So that's essentially the fatigue design. Generally, it's not a very rigorous scheme at here. So what we do is, for anywhere greater than 10 to the power 6, so this is our standard here, we're going to consider it as infinite life. Okay? Yeah, infinite life. And as a matter of fact, later when we design, so if the design thing is design against infinite life. So what that means is you're designing against 10 to the power 6 number of cycles. Is that clear? Yeah, okay. So if you're saying a design against 10 to the power 6 number of cycles or design against infinite life, it's what this means at here, 10 to the power 6. Okay? Yeah, 10 to the power 6. That's a key value of number of cycles. Okay? Okay? So because this is important, okay, this knee point here is important in terms of this steel material. So this particular value at here, okay, is given a special symbol called SE at here. Okay, so now I'm gonna write down a few things at here that we're gonna use, okay, in terms of the notations here. Okay, the notations. So first for SF, okay, SF prime. Okay, I'll explain what the difference between a prime and non-prime means. But when you see a subscript F at here, okay, so what this means is this is the fatigue, okay, strength. Okay, this is the fatigue strength at here. Now this is usually what we do is we use a bracket, okay. So we use SF bracket N, SF prime, or bracket N here. The N is the number of cycles here, right? Number of cycles. So this is the fatigue strength at certain number of cycles. Okay, so that's what that symbol represents. All right, what that symbol represents. So let's say, for example, right? If I look at this figure here, I'm saying, okay, what is here's the data point. Here's the experiment data you obtained from a different trial, and then you see, okay, so what is the fatigue strength at this value here? So what's that value? I'm not sure. Let's take a look at this value here, right? Let's say this value. So at the 10 to the power of 4 number of cycles, okay, and then you draw it out here, right? So that's basically the fatigue strength at the 10 to the power number 4. So let's say this is SF 10 to the number power 4 here, okay, 10 to the power 4. Okay, so this is roughly about 70 KSI in this diagram here, okay, in this diagram. It's okay, that's how you read it. So then there comes to this very simple design problem here, okay, very simple design problem. So if this is the material and this is the SF at this number of cycles, then if I give you saying is, okay, at that moment I'm subjecting the parts, okay, with the cyclic loading of amplitude completely reversed, okay, completely reversed, of sigma A equal to 50 KSI, okay, 50 KSI. Is that okay? Yeah. So then the question here is, what will be the safety factor? What will be the safety factor for design for 10 to the power 4? It has to be specific. So basically, what will be the safety factor, okay, for design at 10 to the power 4? So how would you calculate? So when you calculate safety factors, it's always you compare between two things, right? What are two things? Strength over stress. So what's the strength at this moment? 10 to the power 4. What's the stress? So, okay, 1.4. So you're safe, right? So that's basically this. This is what we call design, right? This is this is actually the simplest case here. It's a design against finite life, right? What's the finite life now? Is 10 to the power 4. Okay, yeah. So the idea is, of course, saying I really just care about the parts within 10,000 number of cycles. That's it, right? You know, other than that, it's the consumer's responsibility now, right? That's okay, right? That happens a lot, you know, when you buy things, 3-year warranty, and then it just breaks right after 3 years, right? So this kind of a situation here, right? You also need to understand here, okay? This diagram here, it's drawn or it's completed, okay, based on a completely reversed, okay, completely reversed stress or loading, okay, yeah. Okay, so that's SF here, okay, that's SF. So then, similarly, you have this SE or SE prime here, okay, SE prime, okay. SE is the value, okay, corresponding to this knee point here, corresponding knee point, okay. So if you look at this SE here, it's actually not anything different from SF. SF is what we call it's a fatigue strength, right? It's a fatigue strength at a certain number cycle. Then the SE is basically the fatigue strength at 10 to the power 6. Okay, that's called fatigue, okay, limit. Okay, so this guy here is also called endurance limit here. Okay, endurance limit. It's nothing different from fatigue strength. It's still fatigue strength. Okay, yeah, but it's a special one. It's a special fatigue strength at 10 to the power 6 number of cycles. Okay, so this is an endurance limit, and what we call, right? Because 10 to the power 6, it will call infinite. Okay, number of cycles, or infinite life. Okay, yeah. And a special case of SF. Okay, SF. SS special case, and you can see it's SF 10 to the power 6. Okay, yeah. Okay, yeah. So finally, what's the difference between primed and non-primed symbols here? Okay, primed. For prime one, okay, that's the result. You generally, if you're using SE prime or SF prime, that's the result obtained from a specimen under controlled lab condition. Okay, so the prime one here is got the result, okay, from, okay, lab conditions. Okay, from lab condition. Lab condition means the part has to be manufactured exactly this size, and the surface has to be machined exactly at a certain condition, right? Temperature has to be also at a certain condition. Okay, so that's called the lab condition. So it's like this graph here. Okay, so they didn't have a prime here, but let's say this is basically obtained from lab experiments. Okay, so that's prime. And non-primed, so as you can guess, so non-prime must be referring to this non-lab condition. So this is the results or some kind of value, okay, for, okay, practical, okay, situations. Okay, yeah. So practical meaning here's a part, you know, anything. It's larger than the lab machine, but it's smaller. Doesn't matter. And it's in the natural environments at certain temperatures, right? Yeah, that's non-prime value here. Okay, non-prime. Okay. Yeah. So then the question here is, right? The question is, I can obtain, okay, I can obtain SE prime or SF prime, okay, under lab conditions. That's okay, right? You know, we can always do something, experiment like that. But what would be this a non-primed value, right? So that's the question here. Actually, that's the value that you should be interested, right? Because that's actually what's going to happen, okay, in the environment. Okay, so your non-primed should be obtained from the prime one, okay, as we're going to show, based on certain corrections, okay, based on applying certain correction factors here. Okay, so the next topic is basically, okay, the so-called, we're going to introduce you some kind of a marine, so-called marine factors. Okay, marine factors. Okay, or simply you can call that, okay, modification factors. Okay, modification factors. And the objective, okay, is to find the SE or SF. Okay, objective is this. Okay, so bear in mind what SE is, huh? SE is endurance limit. SF is fatigue strength. So that's more general concept here, right? More general concept. Okay. So when do you use SE? When you're designing against how many number of cycles? 6, or we call infinite number line, right? And when do you use this? That depends on the question. The question says design for parts against 10 to the power 4 or 5 number cycles. Then that's where you need to basically use these values here, all right? Yeah. Okay. So as I said, we're going to try to get SE, basically SE or SF from SE prime or SF prime. Okay, SF prime. So SE prime, SF prime can be obtained from experiment. And then you can also see that what if you don't have SE prime or SF prime? So basically, what if you don't have the luxury of doing an experiment to get this SE prime, SF prime, right? That's natural. You don't have the experimental data for every kind of material, okay? So then what happens is, or maybe you just don't have the table on hand, right? So then what happens is, generally what we do is we can use an approximation method for SE prime and SF prime first. Okay, so here's the thing here. Step number 1. Okay. So find SE prime. Okay, on SE prime. And so you can either through experiment okay, or you can use approximation. Okay, so this is the formula for approximation in here. Okay, for approximation. For steel, okay, your SE prime is equal to 0.5 SUT. Okay. And that's when your SUT is less than 200 KSI. Okay, 200 KSI. 200 KSI is about 1,400 megapop. Okay, yeah. So that's one way of getting SE prime. As SUT is the ultimate strength of that kind of steel, and those are basically very readily available through the appendix or other resources, right? So when SUT is greater than 200 KSI, and you can simply use 100 at here. Okay, it's 100. So that's SE prime for steel. And there are some other formulas, for example, for iron. Okay, there are also some formula for aluminum, but I will just list this one here. Okay, so SE prime is 0.4 SUT, and that's when SUT is less than 60 KSI. Okay, if it's greater than that, you use 24 KSI here. Okay. Yeah. Okay. Okay. So that's the approximation approach. Okay. In your future calculations or designs, most probably we're going to be dealing with a steel. Then if the question didn't give you SE prime, so just use this one here. Okay. This is probably going to be the most commonly used formulas for SE prime. Okay, yeah. Okay, so that's finding SE prime. Okay. Step number 2, okay, it's to apply the factors, right, to modify it. Okay, so remember the objective is to get SE or SF prime for SE here. Okay, SE prime. So the SE will equal to certain factors multiply this SE prime. So what are we going to multiply it here? We're going to multiply quite a few things that are here. Okay, so KA, KB, KC, KD, and KE, and KM. Okay, so 6 of them. Okay, yeah. So your your training or your lesson, okay, is going to be on how to get each one of them and what are each one of them here. Okay, yeah, some of them very simple. Okay, some of them needs a little calculation. Okay. Is that clear? Yeah. So, but the idea is once you get all the factors, okay, multiply them out, you get your SE. Okay, what SE is SE is the endurance limit, which you will use that in your calculation, in your design or analysis. Okay, for the stressed part. Okay, yeah. So overall, this is what we call what we call the Marin factors. Okay, or correction factors. Okay. So as you can see, this is non-corrected, right? You can also see this is non-corrected, or the lab condition, and this is a corrected. Okay, this is corrected. Okay. Yeah. So now let me elaborate about each one of the factor at here. Okay, as to what are they. Okay. So first, Ka. This is called a surface factor. Okay, it's called a surface factor. So I think what you need to bear in mind is all of these factors here, right? All of these factors are basically, it's what they're trying to do is they're trying to change the condition that is different from the lab condition. Okay, so for example, the first surface factor basically saying is, okay, the one that you use in experiment has a certain standard surface, and then in reality you have a different other surface here. So then what do? We have to modify the surface here. So what we do is we use this table right here to do the modification here. Okay, this table. So this is your table A-6-2. Okay, 6-2 here. So if you look at this table here, let's say the first column here gives you different surface finishes. So there's ground, machine or cold drawn, so it's referred to the same kind of surface, or hard road, or asphalt. Okay, asphalt. So as a matter of fact, when you look at this, the transition at here, right? When you look at the transition and use the basic manufacturing knowledge here, which one do you think has a rougher surface at here? Which one? It must be asphalt, right? You know, it didn't do anything here. Just use whatever's hammered out as it is, right? Yeah. And so this is basically finer surface at here, and this is a more kind of a coarse, okay, surface here, right? That's the transition. Okay, that's transition. Okay, your lab condition, the specimen used in the lab, it has very nice surface finish. Okay, very nice surface finish. Okay, yeah. And how do I use the table here? Is the formula is this. Your Ka is calculated as A SUT to the power of B. Okay, this is your formula. Okay, so, but before you apply the formula, I think you need to establish common sense. Is you're modifying, basically you multiply the Ka, modifying this Se prime, because you have a different surface finish. So in other words, if you modify, what do you think of this Ka value here? Do you think it's going to be greater than 1 or less than 1? Use the common sense, and why? Would it be greater than 1? It wouldn't, right? It has to be less than 1. Then why is it going to be? If this is less than 1, if this is less than 1, means this Se will be less than this Se prime, right? It will be less than Se prime. So why would you apply a less than 1 value to correct that? So I think you also have to bear in mind what are you going to use the Se for in the future, right? You're going to have to use that to compare with the stress. This is your strength here, right? Endurance limit. You're going to have to use that to compare with the stress. So if you, after modifications, become a smaller value, and then you compare these strains to the stress. So basically, you're sort of more conservative, right? You're using the strains to compare with the stress. Okay, yeah. But the question is, this is a fine surface, and this is the current surface finish, and you apply less than 1 value to crack that. So the reason is because, well, let's see here. You have a very rough surface. You know, that's what it is for the parts, right? So if the very rough surface and compared to very fine surface parts, so which one will be more prone to failure? Very rough one, right? So the fatigue one, the fatigue failure. Remember where does the fatigue start? Fatigue process always start from a crack initiation, right? Crack initiation. So if everything is very finely surfaced, very good, compared to the one with the bumps and holes and somewhere in the parts, and I think this second one will more subjected to or prone to a crack initiation for sure, right? Yeah. So that's the reason here, right? As a matter of fact, if I give you an analogy here, actually Da Vinci did the experiment. So let's say you have a very long string, 10 meters, and you also have a very short string, 1 meter, same thing, okay, same material. So which one do you think is going to fail first if you subject it, let's say you hang a ball there and let it swing? The 10 or the 1? And why?
More places that there could be a weaker spot.
Exactly. Yeah. Okay? Yeah, exactly. Okay. So this actually, you'll see that effect in the second factor, KB, which is called the size factor there, all right? Yeah. But for now, the surface factor, okay, and here's the current ones. They're not as good as the lab specimen, so the Ka is going to be less than 1, okay? So if your calculation is greater than 1, you should stop there and recalculate. Okay. So how do I calculate this Ka here? So making use of the table is this. Let's say my SUT given as megapound. Let's say SUT is 520 megapound. Okay. And the part is grounded. It's ground kind of surface. Okay, ground. So given the table here, my A value would be 1.58. And B would be negative this. Okay? Yeah. So substitute the 3 things over here, then you can calculate your Ka, which is approximately 0.9285. Okay, 0.9285. Okay. If you use your calculator, giving the same SUT, but maybe it's machined, the second one here, you'll find the second one, the Ka will be approximately 0.86, so it's decreasing, right? It's going to decrease. Okay, so this is for grounded. Okay, for ground. Is that good? Yeah. So if your SUT or that you're working on, the question is in the standard unit, okay, then you're going to use this one for the A value. Okay. Okay. So that's surface factor. Okay. Yeah. So KB is the size factor. Okay, size factor. For the size factor, that's exactly what I've been saying is, remember that remember the specimen here that I was referring to here. The specimen here has a center diameter right in the center here, 0.3 inch, right? So that's basically the standard size used in the experiment. Then if the actual parts, okay, if the actual shaft or bar, okay, it's not 0.3, it's smaller or larger than that, then we have to apply this KB to modify the SE prime. Okay? Yeah. So here's a KB formula. Okay. There are 2 different formulas for KB. Okay. I guess I need to point out one premises first before I write down this formula. Okay. Okay. So what I need to write down here is for rotating. So first for rotating. Okay, for rotating shaft or circular okay, for rotating circular shaft. Under constant bending. Okay, so what this premises is that this is actually the same premises used in the experiment, right? In experiment, when you use the experiment I showed you there, what was that? That's rotating circular shaft, right? And is that under constant bending? Yes, right? Okay, so in this case, your KB has a formula which is, okay, d over 0.3 at here, negative 1.0, okay, and if you do a little simplification, it's equivalent to write it as 0.879 and d to the power negative 1.07, and this is for d, okay, within 0.11 inch and 2 inch, okay, 0.11 inch and 2 inch. If d is greater than 2 inch, okay, but less than 10 inch, okay, so it's slightly different formula. This is 0.91 and d negative 0.205. Sorry, 157. Okay, 157. So that's KB. This is in US unit here, in inches, right? In inches here. Okay. So I will give you guys a certain set of Excel formula templates. Okay, just kind of reduce your calculations here. In the future, when you design assignments, I've already inserted those formulas in Excel. Okay, now you do have another set of formula when it's for standard unit. I need to point this out because there is a very tricky mistake people can make at here. If you use standard unit, okay, and the first one here, the D is between 2.79 millimeter and 51 millimeter here, and D is greater than 51 millimeter but less than 254 millimeter. Okay, yeah, so this is a standard unit here. If you use this one here, okay, sometimes the question is given is the SI unit, okay, so then you have to use this second one here to calculate the KB. But a very, very common mistake I've seen here is the D at here, okay, the D here is millimeter, okay, when you use this formula here, you have to convert the D to millimeter here, right? Yeah, so remember this one, okay, so D is in millimeter. Okay, because the question maybe give you is a meter, right? So if you keep calculation, use the meter, everything meter, and then keep using the meter, you actually got the wrong answer, right? Yeah. So this is for a rotating circular shaft under constant bending. So that's the same kind of a condition as the lab condition, right? As a matter of fact, you can look at the KB here. So what value is the KB when D is the same as the lab size, 0.3? The KB will equal to what? It's not tricky. 0.3 over 0.3 is 1, so 1 to the power of anything is 1, right? It's 1. So no change, right? No change. Okay? Yeah. Okay, so what if the D is less than 0.3? What do you think the KB is? It going to be greater than 1 or less than 1? KB is less than 0.3. Actually, you answered the question before. So KB is less than 0.3, meaning the actual part is the size is less than the lab specimen. So your KB bigger. Yes, right? It's going to be bigger. So if your D is greater than 0.3, it's going to be less than 1. Okay? Yeah. Is that clear? Yeah. Okay. So in reality, you don't have this same loading conditions or the same kind of rotating condition as the lab. So then what happens is we have to modify that a little bit. I'll draw one scenario that you may encounter in the future is this. You may have a shaft, okay? You may have a shaft, let's say, with a notch in the middle of here, okay? A notch here. So in this particular case, if this shaft is subjected to it's rotating, it's subject to constant bending, then the D, okay, you have to choose this one, right? Yeah, choose this is the D in the formula. Okay, so what happens if the loading, okay, what if the loading is axial? Okay, if the loading is axial, basically it's not a constant bending. Okay, that loading is axial, and then what you do is you set your KB equal to 1. Okay, so that's a different scenario from the lab condition. Okay, that's a lab condition. Maybe I'll insert one little thing at here. Sorry about that. So one more condition to insert it here. If the part is not subjected to a loading, okay, so maybe if it's a stationary shaft, okay, if it's a stationary shaft, okay, but completely reversed, okay, torsion or torque, okay, yeah, if this is the case, so stationary shaft but under reversed torsion, okay, so basically the shaft here, it's the torque goes back and forth, completely reversed, right, completely reversed. Then when you calculate the KB, okay, same as above, okay, same as above. Yeah. If the loading is axial and you use this, okay, you use this. So now what happens is next one is you have a circular shaft. If you have a circular or rectangle, okay, or rectangular, okay, stationary, okay, stationary but basically not rotating, okay, not rotating, subjected to repeated or reversed bending. Okay, yeah, so this is another situation here. So what this situation basically, here's a shaft, circular shaft, right? Here's a circular shaft. It's not rotating, and you're basically like bending the wire, right? Up and down, it's completely reversed, like this. All right? Yeah. And maybe the cross section is a rectangular cross section, right? Yeah. So this loading condition or this condition, working condition, is absolutely different from the lab condition, right? So we have to change this this KB at here. Okay, change the KB. Okay. So what you do is in this case here is the idea is we need to obtain a so-called an equivalent, because you see this in the KB at here. You have a D here, right? You got a D here, and that D referred to is the diameter of the shaft, right? And that D referred to the diameter of the circular shaft. If I wanted to keep using this formula here, then under this condition in here, we need to come up with a so-called DE, so-called an equivalent. Okay, basically the equivalent diameter. Okay, the equivalent diameter. Okay, So how do we get this equivalent diameter? So here's the idea. Without the derivation, I'll just explain the idea here. Okay. If we have a shaft, if we have a circular cross section, okay, if you have a circular cross section, and then you subject the circular cross section, the shaft, with the kind of a lab condition, okay, loading, right? Lab condition loading. So as we know that, okay, you have a bending here, then you can draw, okay, a so-called, okay, 95% of the area here. Basically, right? Remember that sigma. What does sigma equal to? It's equal to MC over I here, right? MC over I. So if I define the so-called 95%, okay, of this stress area, okay, and basically, if this is the maximum, right, on the edges is always the maximum. Right, edge is always the maximum, and you can draw a boundary here referring to anywhere between these two boundaries. It's within the 95% of the maximum. Okay, right? Okay. So basically, the C here, if I look at statically, the C is what? Look at statically is mr over r. That's maximum, right? Maximum. And because it's rotating, right? Because it's rotating, so maximum not just happening at here. It actually could happen on every edges here, right? On the lab condition, okay? Every edges. And I'm not going to take in just the maximum. I'll consider anywhere larger than 95% of that. So you can draw another circle here, right? That's 95. Between this is 95% of area here. Is that right? Yeah. Okay. So this is your lab, right? This is your lab condition. This is your lab condition. Okay? Yeah. So now the condition here is circular rectangular section, but not rotating. Okay? But not rotating. Okay? So but not rotating, only subject to a repeated reversed bending. So which means what? If we have a circular one again, okay, and you subject this bar up and down bending like that, then what will be the area or what will be the location giving you this 95%? You can draw. It will be where? It will be here and here, right? Is that good? Yeah. So the equivalence, basically, you equate this area with this much here for the circular one. If I have this rectangle here, where will be the 95%? It will be between here and here, right? And this is a center, the neutral axis, right? Neutral axis. So you have to equate this portion with that portion. Then, if this is the D at here, okay, the diameter D for the regular one there, okay, for regular shaft, and we can obtain a DE at here, okay, we can obtain a DE. So without a derivation, I'll show you what the formula is, okay. For a non-rotating circular, this one here, the DE is 0.37 D, okay, 0.37 D. So if this is actual diameter D, you're actually going to just have to use 0.37 D for the actual calculation of KB. Okay, yeah. For this one at here, okay, if this dimension is B at here and this dimension is H, okay, then the DE will be 0.808 HB. Okay, HB. So you're going to use this one for the calculation of KB. Okay, for this calculation KB. It's not very commonly saying, or not very common in our case here, and we don't do much of it. Usually we deal with a circular shaft. Okay, yeah. But if you have a loading condition, it's a cross-section rectangle, not rotating, subjected to a complete reversed bending, and then it's a fatigue loading. Then when you calculate your KB, you use your D with this 0.808 HB. Okay? Yeah. Yeah, sorry.
Are we not concerned about units of this? Because they have
the unit, it's yeah. So the yes, you should be concerned because the unit is determined by here. If you're going to use inches here, right? Then this is going to be inch. This is going to be inches.
Wouldn't it be inches squared?
A good point. Exactly. Yes. Excellent. Good. And I didn't make that up, okay? It's supposed to be like that. Yeah. Okay. Was that good? Yeah, thank you for that. So that's Ka, Kb, and then let's look at Kc, which is the loading factor. So the rest of the factors actually are easier now. The only tricky one maybe is just Kb. So Kc factor is called a loading factor. Well, loading factor is it's essentially saying is, what if the part is not the same loading as the lab condition? Right? Lab condition is rotating shaft and then a bending, right? Bending. So if it's bending, okay, then you don't have to do any modification because it's the same as the lab condition. If it's axial loading, okay, then your Kc is set to 0.85. Okay, set to 0.85. Okay, so those are basically empirical numbers. Okay, yeah. And if subject to pure torsional loading, okay, your Kc is 0.59. Okay, 0.59. Okay. Yeah, we will re-examine these numbers later when we are talking about combined loading for fatigue design. Okay, yeah. So we'll come back to these numbers again. Okay, so that's pure torsion. Okay, nothing else but pure torsion. So if you have a so-called combined loading, okay, so combined loading is any combination. It doesn't matter what kind of combination. Maybe it's axial plus bending or axial plus torsion, right? It's combined, and then it doesn't matter how combined it is. You just set your Kc equal to 1. Okay. Yeah. All right. So that's loading factor. And temperature factor. Okay, so those factors are very easy to understand here. Okay, temperature factor. Again, you're going to have to look up the tables for a temperature factor, Kd. Okay, put the Kd out of here. Okay, and this table is 6-4. Okay. So when you use this table, okay, you got to be careful. A couple of things that are here. Okay, there are two columns. One is degree. Okay, the other is Fahrenheit. Right? Yeah. So which one you use depends on the question, right? And it didn't give you all the numbers. You know, if you have a if you happen the question is maybe let's see 320, let's say, right? If ask you is what will be the factor of 320, so then what do you have to do? You have to do a little interpolation here. Okay, do a little interpolation. Okay, if you choose to use the table, then chances are interpolation. And I don't have time anymore, but it's almost finished. If the question is in Fahrenheit, we do have a formula. Okay, we do have a formula. So I'll give you what the formula is, and actually maybe I'll just write it down. It's kind of a long formula, but you don't have to write it. Just remember there's a formula, okay? Just remember it's a formula, okay? Yeah. So the TF is actual Fahrenheit here. You substitute in it, and you get the KD there, okay? You get your KD. Yeah. Any questions? All good? Yeah, so we'll do some exercise in the next lecture regarding each one of the factors. Okay. Yeah.